Good morning all. This is Dr. T. Khalandar Basha, working as Associate Professor in the Department of Electronics and Communication Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss the problems and questions related to Module 1, which is 8086 microprocessor, under the course Microprocessors and Microcontrollers. So calculate the physical address of the following instructions: SBB AL, ES colon DI plus 5A, IMAL AX, memory address generated by SI plus BX minus 8C, and AH, memory address generated by the SI plus 42. And given the values are code segment register as 5000H, data segment register as 8000H, stack segment A000H, extra segment B000H, source index register 2000H, destination index DA register 6000H, base pointer 1002H, stack pointer 0002H, AH is equivalent to 000H, BH is equivalent to 5200H, CX is equivalent to 2000H. So the physical address or effective address is generated by the formula as the segment register contents multiply with 10H. For that we had to add offset. So by this we can generate the physical address which is of a 20-bit size for the following instruction. So the first instruction, the source data exists in extra segment. The offset is given through a DI, plus 5. So first we will see the offset value, where the offset value is the sum of a DI register plus immediate data, that is 5H. So in the given problem, the DI register is 6000 plus the relative value or immediate value as 5H. So the offset value is 605H. So for generating the physical address, we had to multiply the segment register. So as per the instructions given in the example, it is referring to the extra segment. So the effective address is equivalent to extra segment register content multiply with 10H, for which we are going to add the offset value. So in the given problem, the ES value is B0000H multiply with 10H. For that, the effective offset value, which is 605H, we have to add. So with that, we are going to get the value as B0000H add with 605AH. So by addition of B0000H with 605AH, we'll get 0 plus A as A, 0 plus 5 as 5, 0 plus 0 as 0, 0 plus 6 as 6, and so here we will get the physical address is B605AH. So this is how we can calculate the physical address of any given instruction. So we can work out on the remaining two cases, where in the second instruction, if explicitly the segment register is not mentioned, we had to consider by default it as a data segment register multiply with 10H, for which we are going to add SI register contents, BX register contents, subtract with 8C. For second example. The third example, and AH, SI plus 42H So for this, the segment register is DS into 10H plus we are having the offset value as addition of SI register with 42H. This will generate the physical address of the given instruction, that is AND AH comma SI plus 42H. Next, calculate the physical address is represented by, so here whenever two entities are given with a separator as colon, the first one before colon will be refers to the segment register contents colon with offset. So as we know, the address, effective address or physical address we can calculate as the segment register contents multiply with 10H. For that we need to add offset. So we'll work on the first one, where the segment register is 2000H. So 2000 multiply with 10H. For that, we need to add offset. The given offset in the problem is 5000H. So which it is going to give as 20000H plus 5000H, which will rise to 25000H. This is the physical address of the given segment register as 2000 and offset value as 5000. The second one, where the segment register is 5000 and offset value is 2000. So we can evaluate the physical address of 20 bits as 5000H multiply with the 10H. For that we are going to add the offset value, which is 2000H. Next example, next problem. Solve for a memory address for the next instruction executed by the microprocessor when operated in the real mode. The following are CS and IP combinations. So here we need to fetch the address of the subsequent instructions, where in the problem they are given with the code segment register and instruction pointer. So the physical address of 20 bits we can write as segment register, because it is refers to code memory. So where the base address is will place in code segment only. So CS multiply with a 10H. So add offset value for it. So which will give rise to, in the first example, a CS value is 1000H and IP is 2000H. So CS value is 1000H multiply with 10H, for which the offset value is given as 2000H. So we'll get this one as 10000H plus 2000H, which will rise to 12000H. This is the effective 20-bit address, which is the physical address of the next instruction to be executed. So in the second example, the CS value is given as 2000H and IP value as 1000H. So the physical address will get as 2000H multiply with 10H plus 1000. Like that we can generate the physical address for second problem. Next one is develop an assembly language program to sort the given values in ascending order. So here we are going to apply the procedure or algorithm is, if we have the 4 datas which are N1, N2, N3, N4. In the first iteration, we will compare N1 with N2. As it is ascending order, if N1 is less than N2, then don't alter the values. If N1 is greater than N2, then we are going to alter N2 and N1. This is the first iteration, and the N3, N4 will not be checked in the first iteration. In the next iteration, the second data we are going to be checked with the third data. Assume N1 is the smallest biggest value in the given series N1, N1, N2, N3, N4. Because we need to arrange in ascending order, I'm taking N1 as highest value so that it has to go into the last value. So when we compare N1 with N3, again same procedure will apply. If N1 is less than N4, don't alter the contents of N1 and N3. Go for next iteration where we are going to compare N3 and N4. So now, as we have assumed N1 is biggest among all the 4 entities. So as N1 is greater than N3, we have to swap these two contents. So in the second iteration, we will get the series as N2, N3, N1 and N4. So in the next iteration, we will compare the third value with the fourth value. That is N1 with N4. We will apply the same logic. If N1 is less than N4, don't alter these two contents. If N1 is bigger than N4, swap these two contents. So with that, we are going to get the ITR2, that is third iteration, as N2, N3, N4 and N1. So if we have 4 entities, that is in a given series, to arrange or sort the given series, if the number of elements are n, then we are going to get 3 iterations. And here we have checked in these 3 iterations only the N1 value. In the next iteration, we will check N2, the corresponding position in the subsequent values with N3, then N4, then N1. However, N1 already we have checked, so only these two comparisons are followed by these two comparisons. In the next time, we are going to check the N3 position. N3 with N4, this is N2, N1 after this. Then we will compare N3 and N4. So only one iteration, here 2 iterations, here 3 iterations. So like this, comparisons totally will take 3 rounds. So for this purpose, we are going to have 2 counts initialized with the 3. Here also we will initialize with the 3. After next iteration, this will be decremented, that will be paused here. 2 comparisons will be there. In the next iteration, that is third iteration, only 1 comparison will be there. Now we will see the program for it. So as we are executing the programs on assembler, we will request the memory for code segment and data segment using the assume directive. Assume CS colon code, DS colon data, then a data segment. As it is for sorting the series of the values, we are considering 8-bit size, so define byte, and the series value as 65H, 89H, ABH and 52H. So here the values are 4 in number, so that count we are going to be placed as 04H. So in this sorting, once the program is sorted, the sorted values again we are going to exist in the same memory locations. So where we are not going to have the target locations. Then we will end the data index. The first 2 instructions for fetching the address of the data segment and moving indirectly into the data segment register, as immediate data loading into data segment register is not allowed. So first we will move the data, which is a data segment address, into AX register, from AX register to data segment register. Next we will write the ITR. So here in this segments we will write, instead of count, we will take this one as ITR, where the number of iterations are 03H because 4 values are there. So that we are going to be loaded into CL register. For internal iterations, the CL contents will be reloaded into CH register. For pointing to the series variable, for fetching the offset value of series variable in the data segment, we will use the directive offset. So you will write move SI comma offset of series. Fetching the contents of that memory locations, we will use in brackets SI. So move AL comma in square braces SI. Now we will compare the first data with the subsequent data. So we will compare AL comma SI plus 1. Now in this, if AL is greater than SI plus 1, which is nothing but this is first memory location contents, this is second memory location contents. So when we want to swap, if the first memory location content is bigger than the second memory locations, then go for exchange. Otherwise, skip the exchange. So if EL is greater than SI plus 1, then the carry flag is equivalent to 0. If AL content is the second memory location, that is SI plus 1, in that case the carry flag is equivalent to 1. So for ascending order, when this condition is satisfied, go for swap operation. If it is descending order, this condition we have to check. So now here we are checking for JC, that is jump if carry. If carry is equivalent to 1, what it indicates? The AL contents is lesser than the second memory location contents. So no need to exchange. So go for fetching the next memory address. So there we are going to replace L1. So as AL contents, which is a first memory location content, is greater than SI plus 1, we will get carry is equivalent to 0. This condition is fails. So next we will write the subsequent instruction. When this condition is fails, the next instructions will be executed. So what we will write the next instruction says? Exchanging of the data between the first memory location and second memory location. However, in 8086, memory to memory direct transfer is not allowed. So first we will move into one of the register from their memory location. So for exchange of the data, as we know, AL is consist of the first memory location content, SI plus 1 is the second memory location contents. So after executing this, the first memory location contents are moved to the second memory location contents, and second memory location contents are placed in AL register, because the data size we are considering is only 8 bits. But however, this data we want to load into M1. So for that, the next instruction you write exchanging SI with AL. So what is SI? This will be point to the first memory location. What is your AL contents? The second memory locations. So when we do this, the M1 contents, that is memory location 1 contents, will be changed with M. Right. For proceeding for the next byte checking, we go for increasing the address of the series variable. As one comparison is done, decrement CL. So this loop 2 from L2 label to L2 will be executed until the CL is equivalent to 0. So when we are doing this decrement of the CL, so if CL is not equivalent to 0, then the jet flag is equivalent to 0. So then go to loop 2. So what we'll do in the loop 2 is again fetch the contents, compare with the subsequent values, check for greater than or less than. Accordingly, depends on exchange is required, this will be executed, otherwise come to L. So this iteration will be done. So once this CL content is equivalent to 0, if CL is equivalent to 0, then the jet flag is equivalent to 1, then next instruction will be executed. So in the next instruction, what we are doing is second round that we are going to have in CX, that will be checked, decrement CX. So here also, if a CH is non-zero, go to label 3. If CH content is equivalent to 0, the next instruction will be executed. So once the CX is also equivalent to 0, then we are going to terminate the program by calling interrupt 21H, and the function with 4CH will be executed. So move AH comma 4CH INT 21H. Then we will end the code segment by using the end directive, proceed with code, and we will end the program with the directive end. The program is started with the start line. So this is program for ascending order. If they ask for descending order, this you change for JNC. Remaining instructions and program is same. So what is the condition for swapping, and that will be altered. Next, write an assembly language program to find out the number of even and odd numbers for a given 16-bit hexadecimal numbers. So if you are given a number as it is 16-bit B0 to B5, to decide whether it is a even number or odd number, just we go for checking LSB. If LSB is equivalent to 1, we will decide the given number is odd number. If LSB is equivalent to 0, it indicates the given number is even number. So for developing the program for this case, we will take the data, shift or rotate the contents towards right side by 1 bit. So when you shift these contents, this LSB value will be moved to carry flag. So by checking the carry flag, we can decide whether it is even number or odd number. So first we will write assume statement directive, which is for requesting the memory for code segment and data segment. In the code segment, we will declare a series collection of the data. So how many values we are going to check, that we are going to have as count db04h. So once we are estimated the number of entries as even number and odd number, we are going to store that result into these memory locations. Then we will end the data segment using data index. So in the code segment start, the first two memory locations instructions are for loading the data segment register with the data segment address. So this is for clearing a BX register, where BX register we will use 8 bits for odd and 8 bits for even count. So how many values we are going to check, that we are going to be loading to CL register. For fetching the offset value of this series variable in the data segment, we can use LEA instruction, which is load effective address. So the effective address of the series variable, which is nothing but offset of the series variable, will be loaded into SI register. So other instructions we can have like this: move SI comma offset of series. So any one of these instruction we can use, either LEA SI comma series or move SI comma offset of series. So once the address is loaded into SI, we will fetch the content of each memory location into AL register. So now in this case, if it is 8-bit, we will place AL. If it is 16-bit case, for 16-bit case, we will write this one as move AX comma in square brackets SI. Two memory locations will be fetched. If it is 8-bit, move AL comma SI. So this program is wrote for a data size of 8-bit, that we can extend for 16-bit also. In that case, you can change this one to X. Next, once the data is loaded into AL, for checking whether it is even number or odd number, we will shift these contents towards right side by 1 bit. So for that, we will write SHR shift logically towards right side accumulator contents by 1 bit. So when you shift these contents of AL, the B0 bit will be moved to carry flag. So here we will check whether the carry flag is equivalent to 1 or 0. So if carry flag is equivalent to 1, what it indicates? It indicates odd number. So go for incrementing odd counter. If carry flag is equivalent to 0, then it indicates it is an even number. So we go for incrementing even count. So at label 1, so when the control will be transferred to label 1, when the carry flag is equivalent to 1. So carry flag is equivalent to 1, it indicates it is an odd number. So at label 1, we will write a instruction logic for incrementing the odd count. If this condition is failed, then we have to increment even count. So subsequent instruction. So subsequent instruction will write increment BH, where it is for even count, and increment BL, this one is for odd count. As we want to skip this instruction, we will write unconditional jump to LD. Because for a given number, either we have to increment even count or odd count. Then for addressing to the next memory location, increment SI, decrement count because one data is finished. Then J and Z, if CL is non-zero, go for loop 3, where loop 3 is labeled for fetching the data, then shift the contents, then compare with carry flag. Okay. So once this iteration is done, then we will fetch the even count address into BA register. So where we have the even count is in BH register. So the BH register contents will be loaded into the memory location. Then for pointing to the next memory location, as we are given subsequent instruction, we'll write increment DI. Otherwise, here also we can write LEA DI comma odd count. Any one of these two instructions we can write. So in the data segment, as we are declared, these two are subsequent instructions. So instead of LEA instructions, you can use increment DI. So it will point to the odd count. So where we have the odd count, that is in BL register. So BL register count will be placed in that memory location. Then you will terminate the program by using move AH, 4CH, INT 21H. We will end the code segment by using n-directive with the prefix as code. Then we will end the program by using the directive n-directive. So this is the program to find even numbers and odd numbers in a given series. Then we will move to the next program, that is develop an assembly program to find sum of squares. So here also they will give the numbers like n1, n2, n3, n4. We need to find out what is the n1 square plus n2 square plus n3 square plus n4 square. So this is the output which we want to fetch. So for multiplying or finding out the square, we will use the mul instruction. So mul instruction will take only one operand. The second one is implicit operand, which will be there for 8-bit case in AL register. For 16-bit case, it is AX register. So the operand one as well as the implicit operand, both should be same for finding out square. So once this square is done, then we go for declaring a register assigned for finding out the sum. So whatever the result which you obtain after multiplication, that is AL contents will be multiplied with operand 1. The result we will get in AX register, that will be added every iteration. So now we will see the program for it. So first one is finding out for sum of the squares. We will write assume CS colon code DS colon data. Then we will declare the data segment as data segment series DB 65H, 89H, LBH, 52H. As we have 4 entries, we will write count is equivalent to 04H. After finding out the sum of the squares, you will write sum square in the memory location, where it will take 16-bit data. So we can write DB02H, otherwise you can write DW01H. Anyone is valid. As it is only reserving, we will use DUP, and it is for uninitialized, we will write question mark. End the data segment with data ends. So the first instructions for loading the data segment address into the DS register. So for sum, we will clear XR BX, BX. So after this, the BX register count register is equal to 0. For fetching the address of the series variable, we use either LEA instruction or offset directive. So move SI, offset of series. This will fetches the offset value of the series into SI register. Then how many values we want to check, that we will write in the count. Move CL, count. Next, fetch the first data, that is move AL, in square braces SI. So the first data which is in the memory, that will be fetches into AL. Then you write mul AL. So this instruction will multiply the AL contents with AL contents, where the result we can get in AX register. So in this AX register, we have the square of the number that we are going to be added to BX register. So as one number For the first number, we found the square. For checking, for getting the second number, we go for incrementing the address by using increment SI. As one data considered, we go for decrementing the count. So this loop will be iterated until Cx is equivalent to 0. So once all the numbers are squared and added to the Bx register, we have to load the result into the memory location. So for that, we will fetch the address of the sum of the squares variable by using the assume offset directive. So move di comma offset of sum of the squares. So into that memory location, the result which is in Bx register will be loaded. Then we will terminate the program by raising int21h with a function called forch into Ax register. Code ends and end the program by using end start. The next one is develop an assembly language program to perform multi-byte addition. So where we are given with multiple values like this, assume some random data I am taking. So we want to add the multi-byte addition where each data is a multi-byte in the memory location. This we are going to add with the one more data and result will be stored. So here in the data segment we will take a byte series, then byte 2 series. So this is the lower data we will consider, this is higher data we will consider. So here the objective is, first we will add 65 with the 32H, 89 with A6H, AB with the 94H, 52 with CDH. So as the data is present in memory location, this is byte 1 of the series, this will take as byte 2 series. We will fetch each data from each block, then we will add these two values. The result we will get into byte sum. This will be done after all the iterations are done. So for that we are going to reserve, then data ends. Now in the code segment we will write fetching of the data segment register, loading into data segment register. For fetching the address of byte 1 series and byte 2 series into two registers, we will take SI comma BX. Next, DI will have the result address, that is byte sum. How many values we are going to check, that count we are going to be loaded into CL register. For fetching the first byte of the byte 1 series, we will write move AL comma in square process of SI. That we want to add with the contents of second byte. So for that we will write move AL comma in square braces BX, where BX is pointing to byte 2. So this instruction will add the byte 1 series with the byte 2. After addition, the result will be there in AL register. So this AL register we are going to be loaded into the target location. So move in square braces DA comma AL. Then for pointing to the next byte, increment SI for byte 1, increment BX for byte 2, for the result increment DA. As we are done one byte addition, we will decrement the count. So this repetition will be takes place addition until the CL count is equivalent to 0. Once the CL count is equivalent to 0, all the data is added and it is moved into the destination location. So we will end the program by generating int21h with a function called forch. Then we will terminate or we will end the code segment with the code ends. We will end the program by using end start. Next, interpret the functionality of the following pins. ALE. ALE stands for address latch enable, where this a pin will distinguish whether AD0 to AD15 consist of address or data information. So if ALE is equivalent to 1, the AD0 to AD15 will contain the address information. If ALE is equivalent to 0, then AD0 to AD15 will contain the data information. Next, DEN bar, which is a data enabled, which is like a status signal. So whenever this DEN bar is equal to 0, it indicates the valid data is present on the data bus. The next one is BHE bar, which is bus high enable, which is for differentiating whether higher byte of the data, either it may be 8-bit case or 16-bit case. If you are referring for higher byte, then BHE bar is equivalent to 0. It indicates we are accessing the upper data. Either the data size may be 8 bits or 16 bits. When BHE bar is equivalent to 1, we are going to be refers to lower data only. So this 8-bit or 16-bit transactions will be done by using BHE bar and AG. The next pin is ready pin. It is the status signal from the slow response device. So when now ready is equivalent to 1, it indicates the slow response device is ready for data transaction. So the processor will have the communication between the slow response device and the processor. Either it may be read operation or write operation. So it is corresponding to IO device. Illustrate the following arithmetic instructions of 8086 microprocessor with detail. SBB. So the syntax of the instruction is SBB, destination comma source. This instruction will subtract the destination contents with the source along with the carry flag, and the result will be sent to the destination. Subtract the source contents from the destination along with the carry flag. The next instruction is DAA. The syntax of the instruction is DAA, where it is a 0 operand instruction. All are implicit operands. So this instruction we have to perform after addition operation. After addition, the result should be exist in AL register. Then we will check the lower 4 bits. If the lower 4 bits are greater than 9, then add +6 for it, +6 to AL. After checking the lower 4 bits, then we'll check the upper 4 bits of AL register. If it is greater than 9, then add +60 to AL. If the lower 4 bits is less than or equivalent to 9, don't enter the contents of AL. Similarly, upper 4 bits are less than or equivalent to 9, don't enter the 4 bits. So this DA instruction, it is mainly for converting the data which is in hexadecimal into packed decimal. The next instruction is DIV, which is unsigned division operation. The syntax of the instruction is DIV operand 1. It is only one operand instruction. The second operand is implicit operand. So in 8086 processor, there are two cases exist for division operation. The first one is the 16-bit data we can divide with 8-bit data. The second case is the 32-bit data we can divide with 16-bit data. So whatever the dividend is there, which is a 16-bit size, that will be there in AX register, whereas the divisor, which is 8-bit, should be there in the operand 1 position of the instruction. After executing this instruction, then we are going to have the remainder is in AL register and quotient is in AH register. Similarly, when we are going for 32-bit by 16-bit division, the 32-bit we are going to have in a DX AX pair. Then the 16-bit divider we are going to have in AX register, operand 1 position of the instruction. After division operation, we'll get the quotient and the remainder in AX DX register. DX and AX. Quotient in AL and AH. Here also quotient in AX and remainder is in DX. Next instruction is mul instruction, which is unsigned multiplication. The syntax of the instruction is mul operand 1. It is also single operand instruction. Here two possible cases are there for multiplication. One is 8-bit multiply with 8-bit. One of the 8-bit multiplicand we are going to be loaded into AL register. The multiplier will be there in operand 1 position in the instruction. After multiplication, the product which is of a 16-bit size we can see in AX register. The second case is we can multiply a 16-bit data multiply with a 16-bit data. The multiplicand we can have in AX register. The multiplier we can have in operand 1 position of the instruction. So after multiplication, the product which is of 32-bit size we will get in AX DX register. AX register will contain the lower 16 bits, that is B0 to B15, whereas the 32-bit result, the upper 16 bits, that is B16 to B15, we can have in DX register. The next instruction is ADC, which is for add along with carry. The syntax of the instruction is ADC destination comma source. This instruction will add the contents of destination with the source along with the carry flag, and the result we can have in destination. The next one is AAA instruction, which is ASCII adjust after addition. It is a 0 operand instruction. This instruction is used to convert the result after addition, that is sum in AL register, into unpacked basic. Here the various steps it will follow is, first one is a clear upper 4 bits of AL register. Second one is check lower 4 bits of AL register. If lower 4 bits of AL register is greater than 9, then add 6 to AL and increment AH register. If lower 4 bits of AL register is less than or equivalent to 9, don't alter. No alter the contents of AL or AH register. The next question is illustrate the following data transfer instructions of 8086 microprocessor with the details. Out instruction, exchange and push instruction. Out instruction, it is for write the data to a port. The syntax of the instruction is out port address comma AL, where the port address we can specify in a DX register or in the instruction. So whenever we want to write the data to a IO device, we use out instruction. The next instruction is exchange. This exchange instruction is XCHG operand 1 comma operand 2. This instruction it is for swap the data between operand 1 and operand 2. The next instruction is push. The syntax of the instruction is push operand 1, where the contents of operand 1 will be placed onto the top of the stack. Illustrate the following logical instructions of 8086 processor with example. SHR, which is logical shift right instruction. The syntax of the instruction is SHR, the operand 1 comma count, where the operand 1 is contents of which we want to shift, and count will specify how many bits we want to shift. As it is SHR, the contents will be shifted towards right side. If I have 8-bit data, that is bit 0 to bit 7, so after SHR, this B0 will be there in carry flag and B1 will be get as LSB position. B7 will be placed in next bit to MSB and MSB is appended with 0. The next instruction is ROL, which is rotate left without carry. The syntax of the instruction is ROL, operand 1, count. This instruction, it is for rotating the contents towards left side depending upon the count. So let us consider here we have 8-bit data. So B7 to B0, assume the operand 1 is 8-bit data and we want to rotate for only one time. So as it is ROL instruction, this B7 bit, that is MSB, will be moved to the carry flag. B6 will be sit in MSB position. B0 will be occupies the B1 position, and the B7 will be placed into, as it is without carry, B7 will be placed in both carry flag as well as LS. The next instruction is logical instruction XOR. The syntax of the instruction is XOR destination, source. Here the contents of source will be XORed bit by bit with the destination, and the result will be there in the destination. Explain the following string manipulation instructions. The first one is load a string byte. STOS is for store a string bytes. So load a string byte and store a string byte. It is for exchanging the data between AL to the memory register. Next one is CMPS, which is for compare string, where one string is compared with the second string. So this CMPS instruction we have to prefix with either REPZ or REPE, otherwise REPNZ or REPN, depending upon when we want to go for comparison. If these two data are equal, then go for second data, then prefix with REPZ or REPN. If these two data are not equal, then only go for second comparison, then we go for REPNZ, REPN. So as it is for comparison for equality, usually we will prefix with REPZ or REP. Interpret the significance of flag register of 8086. So in 8086 processor, we have a 16-bit flag register with the 9 active flags. The first is carry flag. So the carry flag will signifies whenever we do the addition operation or subtraction, whether any carry is generated or any borrow is taken, then it will be reflected in the carry flag. If any carry is generated or borrow is taken, the carry flag becomes 1, else it is 0. The next bit is P. P stands for it is parity bit. So the parity bit will signify how many number of ones are there in your data. So as 8086 following the even parity case, the parity bit is equivalent to 1 in the P position if the number of ones in the data is even. If the number of ones in your data is odd, the P bit is equivalent to 0. The next bit is auxiliary carry. This auxiliary carry will be set whenever any carry is generated or any borrow is taken in the lower nibble of your data. If it is in MSB, carry flag. If it is in lower byte, lower nibble, auxiliary carry. The next flag is 0 flag. This 0 flag will be set when the result is 0. If the result is non-zero, then the Z flag will be reset. The next bit is corresponding to sign flag. The sign flag signifies whenever we do the subtraction or any sign data, whether the result is even positive or negative will be reflected in sign flag. If the result is a negative, then the sign flag will be 1. If the result is positive, the sign flag is equivalent to 0. The next one is a trap flag. This is high priority interrupt we can take. For every instruction to be executed, then the T flag should be 1 before executing the instruction. Once the instruction is started executing, the trap flag will become 0. At the end of execution of the instruction, automatically the trap flag is equivalent to. The next flag is corresponding to interrupt flag. If any interrupt is generated to the microprocessor, that will be indicated on the interrupt flag. If no interrupt is generated, then I is equal to 0. So after executing every instruction, the processor will check whether I flag is equal to 1 or 0. If I flag is equal to 1, again if it is, whether it is a maskable or unmaskable, then ISR will be executed or subsequent instructions will be executed. The next flag is corresponding to directional flag, where this directional flag is mainly used for a string manipulation instruction, how we want to process the strings, whether from lower address to higher address or higher address to lower address. So for every string manipulation instructions, we have to modify the direction flag. So if direction flag is equal to 0, then the string manipulation will be takes place from lower address to higher address. If the direction flag is equal to 1, then the string manipulation will be takes place from higher address to lower address. The last flag is overflow flag. So whenever the result size exceeds the given size, then the overflow flag will be set. Wherever X indicates there don't cares, so no significance for the bit positions with X. Illustrate the following control transfer instructions used in 8086 microprocessor. Loop. The loop instruction, it is for a repetition of the execution of the instruction from the label specified to loop instruction. So how many times this instruction will be executed will be depends upon the count which is in CX register. The next instruction is RET, where RET is the last instruction we have to write in any subroutine indicating the processor written from the subroutine. The next one is INT instruction, where INT instruction, it is for generating a software interrupt. The syntax of the instruction is INT type, where the type is 8-bit size, where this type will takes from 00 to FFH. So total 256 different types of interrupts we can generate by using INT instruction. Outline the following addressing modes with example. Base indexed addressing mode. So here in this addressing mode, two offset values we have to place. One is base and the one is indexed. So the offset value we are going to be placing one of the GPR, that is BX. The next one is one of the index register, either SI or DI. Then we can write some instruction like move instruction. So now here we have two offset values. One is in base register, the second one is in index register. The next in addressing mode is relay to register addressing mode. So in the relay to means some offset value we had to write in the instruction. Register means some register we are going to take, that is a general purpose register for having the offset value that we can load into some register, the move or add any instruction. Next one is register indirect addressing mode. In the register indirect addressing mode, the offset value will be loaded into any one of the general purpose register. Then that will be placed as a source data. Then it is called as register indirect addressing mode. Outline the following addressing modes with example. Direct addressing mode. Direct addressing mode means if we have the address directly specified in the instruction. When our square braces indicates it is a memory location, if the address is placed directly in the instruction, then it is called as direct addressing mode. Next one is relay to base indexed addressing mode. So here total 3 offset values are there. One is relative value, base value and index value. So 3 offset values like 50H, one offset value in base register, another offset value in some index register. This we want to load to some register as well. So how many offset values we have here? 3 offset values. Relative, base and indexed. Next one is indexed addressing mode. This is indirect way of referring to a memory location. The data is there in the memory location and the memory address is exist in index register. So you'll write like move AX comma in square braces S. So BSI will hold the address of the memory location where the data is reside that we want to move into AX register. So these are the various few questions under module 1 of 8086 processor. So thank you. In the next session we will see the subsequent units. So in this session we have discussed a few questions related to module 1. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.